Welcome everybody to our monthly Gordian Blockchain Commons and wallet interoperability meeting. Um, so first, what is Blockchain Commons? We're a community interested in self-sovereign control of digital assets. We bring together stakeholders to collaboratively develop interoperable infrastructure. We design decentralized solutions where everyone wins, and we are a neutral not-for-profit to enable people to control their own digital destiny. Uh, we are only able to do this work due to the support from our sponsors. These are some of our recent sponsors. Um, However, I have to say it's been a tough year. We've lost a number of sponsors. They remain interested in our tech, but they are having their own problems with funding, whether or not it's getting the next round of their financing or other challenges. So definitely if you're able to be a sponsor, please contact me or you can directly sponsor us on GitHub. But we can also support your company on specific projects that are related to our work. Um, if you're interested in this, talk to us. In particular, I wanted to thank Human Rights Foundation, who basically offered us a grant to continue some of our Frost workshops and work, and Foundation Devices for our recent Gordian Sealed Transport Protocol funding. So thank you very much, Foundation Devices and HRF. We also appreciate our individual sponsors. Um, uh, Really, what this does is show that there is a community of developers out there that are following us, and it helps organizations like HRF and other grant organizations to know that we're legitimate. So, our slide here, I'd like to see more on the top than on the past. So if there's any way you can support us as an individual, it would be greatly appreciated. Uh, how to continue to be involved. We have a number of different channels to be able to communicate. They're all on this blockchaincommons.com subscribe link, including getting emails about the Gordian developer meetings, the one you're at today, but also our other workshops like our Frost workshops, etc. This is an announcements only mailing list. For broader discussions, we have a private Signal channel. Just ask to, click on the link and we'll add you. I can also add you to the Google Calendar invites to Gordian meetings. No way to automate that easily, so just send me a mail and I will be glad to add you. At our last meeting, we had a presentation on PayJoin, and we discussed a little bit about what's going on with SSH envelope, which we'll be talking about more. And we talked about request response and why there's some real power in the request response paradigm and how much that can improve the user interface of our tools. Really, maybe less user interface, but more user experience. The table that we showed how many interactions with the user could be simplified or made more direct. So if you haven't seen the request response use case video, it's on YouTube. And it definitely informs sort of some aspects of the upcoming meeting where we're talking about GSTP as a way to do request responses. Today, we're going to be talking about a update. We've had Seedtool was one of our first command line tools for interoperability. It was a reference tool. And we use the CLI tools a lot to test our code and to test our interoperability. But it was written in C++, which was more challenging. I think the world is moving more to Rust, so we did a major move over Seedtool to Rust. We'll be talking about that more today. And then I wanted to talk a little bit about why we're supporting SSH. And Wolf will be sharing with us about the new SSH envelope command line updates. And then we'll close the meeting with a presentation on the Gordian Sealed Transaction Protocol, and hopefully some discussion about what are its implications, because I think it's a very powerful tool that there really aren't any alternatives for. Seedtool CLI, it's available now. It's updated to our newest specifications. There's a new user manual. Wolf, do you want to go ahead and take over?
Yeah, good morning, everybody. I'm Wolf McNally. I'm the lead researcher for Blockchain Commons. I write a lot of our specifications, and I write code to go along with it, as well as libraries that are open source and freely available, as well as tools which anybody can use that actually both showcase, exercise, and make available our technologies to everyone. Let me share my screen here. You should be seeing my browser window here. Some extraneous windows out of my way. So this is the Blockchain Commons GitHub account, our Seedtool CLI Rust repo. And we have, if you search our account for Seedtool, you'll see several different things called Seedtool. One of them is the original C++ Seedtool command line tool, which Christopher's mentioned, which we've now deprecated. Another is this tool that you're looking at right now, which is the new Rust version, which we'll be adding all our features to going forward. And the third is Seedtool for iOS, which is a fully featured, very user-friendly iOS app, which is available in the App Store as well as fully open source. Generally speaking, seeds, for anybody who's not completely familiar with this, who might be watching on YouTube or whatever, seeds are cryptographically strongly generated numbers, which can be used to derive all kinds of other objects, private keys, Bitcoin addresses, things like that. We have always felt that this is a natural starting place, a kind of a root of the tree, if you will, for various kinds of cryptographic operations, including those used by Bitcoin, but also just generally for other cryptographic techniques. So here we're discussing the deprecation of the seed tool. Using the Rust tools, you have to install Rust itself, which there are instructions readily available. Just Google install Rust, and you'll see very easy step-by-step instructions to installing that on your system. After that, use the Rust tool cargo install Seedtool CLI, and then from then on, you can just basically say Seedtool, and it will do it. Really briefly here, let me actually, I'm going to spend most of the time in the browser in this, even though I can switch to my terminal, and I will for a little bit later. I mostly want to switch this.
Why don't you show the manual also?
Yeah. So the actual manual, which Shannon just finished and wrote, is here, and this is a very thorough treatment of everything in Seedtool. There's also a more brief overview document, basically describes use cases. You want to create a seed, you want to import a seed from another source, you want to translate a seed to a different form, you want to back up a seed using SSKR, which is our sharded secret key reconstruction, which allows you to do social key recovery by splitting your key or your seed into several pieces and giving it to your associates, and then a quorum of those shares is required to restore, but nobody individually can restore from their shares. Or you want to create a seed envelope. And we'll be talking about envelope quite a bit today. Envelope is a Gordian envelope. It's a general purpose hierarchical container that supports a lot of very advanced and necessary these days cryptographic techniques like elision, as well as can be used for redaction and other purposes, as well as compression and encryption and various kind of things like SSKR. So we also support an envelope form of seeds. So the manual discusses installing the seeds, generating seeds. Now you can generate seeds using the built-in cryptographically strong random number generator, or if you want to entirely control that the seed is generated from random sources, you can actually flip coins or roll dice or draw cards from the deck. And the tool actually supports inputting those forms directly to use as entropy for creating the seed. Obviously, seeds are very sensitive. You don't want to reveal seeds. So you want to make sure that you have seeds that are your seeds are kept safe and backed up. And so, of course, we support SSKR as one form of backing them up. We also support BIP39, which is a very well recognized, as well as bytewords, which is a form that we use. So, we want to basically, make it very easy for people to control their very private data like seeds. And that's what Seedtool is all about. It's about generating and transforming seeds into other formats that are useful, including backup formats like SSKR. Very briefly, if you just type Seedtool, you'll get 16 random bytes or 128 random bits generated cryptographically strong as hex. If you actually want to input like coin flips, use it in bits, and this becomes a entropy, which is then stretched to create the data that outputs. And so obviously the more the better when it comes to entropy, because like 1 bit, there's only 2 possible output values. Whereas, if you flip a coin 32 times or 64 times, you have much better entropy to use. Same thing with cards. You see, 6 of clubs, 9 of spades, 8 of clubs. So you can just draw cards repeatedly from the deck, shuffling the card in each time and get very clean entropy. So you can get much better entropy. You can also tell it how big the seed you want it to be by specifying count. You can store a seed as BIP39 by inputting it as hex and outputting as BIP39. This is exactly what you would use to replicate the seed in many tools that allow BIP39 input. You can turn a BIP39 mnemonic back into hex. And this is compatible with all the other, systems that use BIP39. Byte words are 4-letter words. There's a vocabulary of 256 words. We use this in our UR format. Each of these two-letter combinations, LP, that's the first and last letters of one of these words. So each of these words represents a byte. But this is the human readable form of that. And so it allows transportation. This is byte words. This is the byte words format. So if I put the input format is these byte words, then the output format is hex by default, and so on. And we support metadata. So you can tag your, if you create an envelope form, because envelope is very flexible in terms of very powerful nested metadata, if you like. You can say that the seed tool, you're going to create a seed, but you want its name to be my seed, a note, and a date for a creation date. And this is the actual envelope, UR:envelope. These are the byte words that make up the envelope, which is at its root CBOR, which is the concise binary object representation language. Kind of think JSON, but binary. But we have an output format. We say envelope format. This is our envelope tool, which we'll be discussing a little bit more later as well. Where we say envelope format, we feed the same envelope back into it, and we get a much better human readable form of this, where an envelope is a subject, in this case, the 16 bytes of the seed, with a set of assertions on it. For example, a type declaration is a seed, the date it was created, the has name declaration, which is we've given here, and the note. So envelope, again, supports very rich metadata, but it focuses all on the subject, which is the actual seed itself, which is very easy to extract and use just for its own purposes. We also support SSKR, Seedtool out SSKR groups 2 of 3. So this splits the envelope given into, actually in this case we're basically generating a new seed and splitting it into 3 shares, any 2 of which can be used to reconstruct the original seed. You can do the same thing with byte words if you wish to have human readable words and so on. So the whole idea is to have a very fully featured command line tool. And like I say, our C++ tool had a lot of this functionality. Going forward, our Rust tool has all of it. And we'll be talking a little bit more about our Rust stack later in this conversation. But question? All right. Well, anyway, I think that's mainly what I have to say about.
Hank had a question.
Okay, please.
Yeah, I had a question about the input of the Seedtool command. If you stretch a certain input into an output and you use that input over and over again, will it always stretch into the same output? That's my question.
Yes, but you don't do that.
Right.
When you generate entropy, it's a single use thing. We have, as you can see here, we have a deterministic flag, which you can input a string, and that is stretched using the hash key derivation function to the full length that you request, in this case 64 bytes. As this suggests, we only want you to use this for testing purposes, because an actual seed uses real entropy generated and used only once. So
of course.
yeah. So yeah, I mean, but yes, once the core entropy is generated, then obviously the quality of the entropy is going to make a difference. But if you use the same entropy again, you're going to get the exact same seed. So the entropy itself should be used once and thrown away, and the seed itself should be kept very secret.
Yeah, I mean there are two main uses. So you absolutely can compare this to, say, Ian Coleman's seed tool on which is a web page. We will generate the same values from the same if you have the entire entropy, it will generate the same values. That being said, you can still make mistakes, etc. So we recommend that only for testing the tools to make sure that your wallet, which maybe is written in Java, is not having any problems with the with the code, and you can test it against Ian Coleman's, etc. Similarly, there are situations, in particular with SSKR, where there's additional randomness that is initialized. That's actually for each individual share. So every time you do SSKR, it's completely different value. And that's the other place you can use the deterministic flag to basically make sure that every time you do the SSKR split, you're getting the exact same value. So there's a lot of detail in here. You can definitely, if you compare, say, Seedtool command line versus, say, the iOS app, the iOS app is gonna, it has a lot more effort in it to make sure that you do the right thing. So for instance, if you don't have enough randomness to completely be 128 bits, it'll warn you, and there's a little button that'll say, hey, I want to fill in the rest of the bits to make sure I at least get up to 128. And it will fill it for you. But then once you've reached 128 bits of cards or whatever it is, can't really do that on the CLI interface. So it really is a more advanced tool, and thus as much as we can recommend people be careful, we always have to say so again. And you want to add
command line
any
tools have always been sharper tools than GUI apps. So
Yeah, I
And the
was just
manual
asking
does
because
say the manual does say how much to use for everything, for all of the coin flips, card draws, etc. It's a simple formula.
okay, that's
But
great. I was just asking because, of course, I know you need to diversify all the time. Every time use another randomness if you're working in production. But for presentation purposes and also learning purposes, it comes in handy that you put in exactly the same randomness to see whether it all works. So
Yep.
that's the reason why I asked.
Yeah,
right,
and
which
that's
is why we
what the
have the
deterministic flag is for.
Yeah, exactly. Yeah, that was good news. Thank you.
And there are situations maybe where you want like a series of random things based on the same entropy. So sort of like BIP 85, I guess, where again, it might be useful to have like, here's my initial entropy, and then now I have the 10 random values that I need for whatever application that I'm using.
We're talking about BIP 85 only a tiny bit right after this. Actually, is there anything else, Wolf, that you're
not on Seedtool?
Okay, so let me just quickly come back to here. So where are we with Seedtool? So Seedtool at this point, I consider it it is not just a test release. I think we now are saying, hey, it's, ready. You can, the previous seed tool had a security review on it. And this one does not. We need to pass the hat at some point to get the same level of security review that we had on the previous libraries for the Rust libraries. But other than that, I do believe it is feature complete as compared to the old Seedtool CLI. However, there are new features in this, and in particular, you saw that one of the big advantages of Seedtool CLI and Rust is that we now support SSKR envelopes, which allows us to have the metadata like, putting in a note in there, etc. There are a few features there that we're not quite sure what the right way to implement is. One of which is that the Seedtool iOS app also allows you to attach a descriptor, which is a well-known DC bore values, so that we can consistently export whatever the Bitcoin descriptor is. And that's very useful if you're trying to, in a multi-sig situation where you don't know which public key this applies to in some taproot complex descriptor, you can put the descriptor in there. So that's very valuable. We're trying to puzzle out what's the right way to do that with the CLI version of it. We're open to ideas there. But we also have this concept of an attachment that allows wallets to be able to put in data that is not as well known as, say, descriptors are, which could include proprietary data, like, this is, some state value that we want to store so that when you restore, the counts are the same as your old wallet's counts and things of that nature. All of those things are defined as attachments. And again, we don't quite have a good idea for what, people need in the attachments and what the command line what are the affordances in a command line version of something with attachments? Because the whole point of attachments is we don't know what they are. We're not supposed to know what they are. They can be anything. Foundation devices can have something very, very specific that they don't have to worry about interop, but they want people to be able to back up. That's a good place for attachments. So, what's the right thing to do when we receive one, or if somebody wants to add one purely from the Seedtool CLI? So that's an open question. No commitments at this point for either of those, but we're definitely looking for input. It has also been suggested that Seedtool should support BIP85, which raises some interesting complications because we have another tool called Keytool that does do some derivation stuff. But BIP85 is kind of a weird hodgepodge. It's only really used by the Bitcoin community, could be useful beyond that. So we've invited the person who has taken over the BIP85 draft on Bitcoin Core to present next month. So we'll have a greater discussion about BIP85 and the implications for not only Seedtool CLI, but our entire stack next month.
Just a quick point of clarification, if I may, Christopher.
Sure.
The Gordian envelope allows you to, again, there's a subject with a set of assertions. Anybody can place an assertion on an envelope, an additional assertion, and republish that. That's totally capable. The whole point of attachments is to create a well-known framework for third parties attaching data to envelopes where they're acknowledged as understood to be either documented, in which case there's a URL where you can actually go and see where the documentation for the attachment is, or undocumented, in which case it's entirely proprietary and you might be able to reverse engineer it or you might not. But the point is it's there and designed to be understood to be ignorable if you don't know what it means. And so whereas other assertions placed on envelopes could be anything, and you may want to just reject them outright rather than say we accept attachments even if we don't understand them. So
I mean, if you're backing up a Trezor key, and you're using it for some NFT on some other blockchain, a descriptor isn't useful. So you can just ignore it. But then you may have some other things you want to store about that NFT or its script or whatever that is unique to your particular wallet's capabilities. You'd basically put that into an attachment. So that's an example of the flexibility that we offer. Any questions on Seedtool CLI or advice, or what would you like to see it do?
So
Go ahead.
I'm not an expert in ARC and all these new things that are happening on Bitcoin in terms of, but essentially they deal in like pre-signed transactions where you need to know the state of the pre-signed transaction. So your wallet balance is basically a secret and some pre-signed transactions that you can redeem. So I guess these pre-signed transactions would then be something that you could put as an attachment, but they would need to be backed up constantly for each time you make a transaction, I guess.
Yeah, exactly. And
But
that's
it was like, yeah.
that is exactly what attachments are for. And then you will see in the GSTP stuff that we're coming up with, which, the primary client for GSTP is backups. You would then be able to have an attachment within a request response that is then encrypted and authenticated to a backup server that you can have a persistent connection with over time. Every time your wallet changes, it shards it to the 3 servers or whatever methodology you've got. So those are all, that's, absolutely in the design to be able to support, those kinds of things in the future. So, yes.
And that would be something to maybe keep an eye on as well as they develop how to sort of get them to trend towards using a standardized way of storing state instead of inventing their own, or yeah.
Exactly. And that's why we try to get as many wallet vendors at these meetings as we can and record them if they're not able to be here. So as far as I know, we're the only people that are really being open and trying to do this as an open standard. There are obviously Ledger shipped their somewhat controversial seed recovery technology. But it's, they chose who you can recover with, and exactly what their trust model is interesting choices. And, we don't believe that you should be locked into a single organization's choice. And we're seeing this trend now. Oh, well, we have to offer what Ledger offers, so we're going to have our own proprietary set of choices. So, yeah, we definitely need to see some more openness on this. Let me move on to the next one. So I want to first mention why SSH. So we've just released a major update of Envelope CLI that, in addition to the keys we already have, offers SSH keys. And so I needed to talk a little bit about why SSH. So traditionally, SSH keys have been used for authentication. Anybody who's done a direct connection to a Unix box or whatever from a remote Unix box has used SSH keys. It's been around for a long time. It's mature, a lot of security reviews, et cetera, on it. It's not perfect, but it's broadly deployed. But for the past 2 or 3 years now, they've been used for code signing. It was built into Git at least 3 years ago, and GitHub and GitLab and several of the other services now enable you to use this. And what this means is that you don't necessarily have to use PGP anymore to sign your code. But not just sign your code, sign your commits, your tags, be able to make other kinds of proofs about your source code base. And we have an open source thing called Gordian Server, which basically installs Bitcoin Core on Macintosh or on a Unix system and installs Tor and does a lot of these other different types of things for you. You know, we've just been frustrated with the whole PGP signing you know, techniques. PGP is now what, 34 years old? It'll be 35 years old next year. You know, it's a pain. So we really want to modernize how we secure our code bases. And this basically would allow us to be able to offer an alternative and to be able to do more with software supply chain, including our own software supply chain. You know, I would like, say, if we hire radically open software to do security review of some of our source code base, they ought to be able to say, hey, you know, these commits and these files are have been reviewed by us as of this particular version. Envelope has absolutely the capability to express that very, very precise statement. And we'd like to see more of that, at, you know, at minimum for our own tools, but hopefully others will be interested. It also demonstrates something important. You know, we've been saying probably since the day one of Envelope that we really wanted to not necessarily have you know, what is sometimes called cryptographic agility, but more about cryptographic flexibility. Like we're not locked into any one particular approach. We felt like this also demonstrated our flexibility by supporting SSH. And Wolf, do you want to take over from here and explain what we've done?
Okay. So let's see, what's the proper place here? Okay. So this is our repo for our BC Envelope CLI Rust. Again, in our account, BC Envelope CLI Rust. This is also available on Greats.io. You can just do a cargo install BC Envelope CLI, and from then on, it's available as Envelope. Again, you can start with the same Envelope help. Now, this is not a new tool. We've had this for a while. But what is new in this is our ability to sign envelopes using SSH keys. And to support that, we started out with we added a new chapter to our documentation. There's a fair amount of documentation chapters here, but we added a new one just on signing, where we start out by discussing the various signing algorithms. Now, the one that we prefer and the one that is the default is still Schnorr signatures, which are based on elliptic curves. We've also supported in our stack, in our Rust stack, ECDSA, but now that's actually available in our API, or in our tool API as a separate option. Again, but unless you have a specific reason to use any of these other formats, Schnorr is fine, and Schnorr is the default. So if you sign an envelope and you don't specify a particular kind of signing key or a particular kind of algorithm, then you'll get a Schnorr signature, and that's great. But we do support these various signing algorithms that are all prefixed SSH. These are the exact same signing algorithms used by SSH Keygen, which is kind of the go-to tool for manipulating SSH keys. Then this document goes into the various kinds of signing primitives. We mentioned seeds here. We do support URSeed, and this is, again, we just talked about Seedtool a minute ago. Seeds are not signers or verifiers. They're not used directly to sign or verify, but they're used to derive other objects. And in fact, you can use seed to derive some of these other objects. In fact, there's a derivation chart here, which shows what you can derive. You can either, our envelope tool can use random numbers, cryptographically strong random number generator to generate a private key base, or you can provide a seed, which will, based on the seed itself, generate the same private key base. We go into what these various objects are, the private key base, the public key base, and as well as the more specific signing private key and signing public key. The important thing to remember is, and before, in our previous release of the tool, you can only use this priv keys and pub keys, the private key base and the public key base, to sign and verify envelopes. Now you can also extract and use the signing private keys and signing public keys, and that's because they are tuned to whatever signing algorithm you specify. Whereas private keys directly signs and verifies Schnorr only. And the public key base is actually a bag of 2 keys, which contains a signing public key and an agreement public key. And this document only mentions the agreement public key in passing, because that's used for cryptography, for actually public key cryptography, primarily. Whereas the signing public key is used for the main subject here, which is signing and verification. So, then we talk about the difference between what we call signers and verifiers, because as you can see, these private private key base as well as a signed private key can be used as signers, whereas they can all be used as verifiers with certain restrictions. Like again, the private key base can only be used to sign and verify Schnorr directly, but if you can derive other things from it that can be tuned to the algorithms you want. And again, most of the time, unless you are really care about using SSH keys for a specific reason, like the things that are forthcoming in our work with Git and GitHub, then you don't need to worry about a lot of these things. You use it pretty much like you always did to sign and verify it. So, here we are showing a simple example of an envelope, this is just the envelope. This is the subject. It's a string Alice. There's one assertion, knows Bob. I always have to emphasize, and we'll see this later when we talk about GSTP, Gordian Sealed Transport Protocol, that this is what's called envelope notation. It's not JSON. It's not anything else. It's actually just a human readable format of the binary structure that is envelopes. And you'll always see a subject at the top, and then if it has assertions, a pair of square brackets, and then the predicate object pairs, which are the assertions. And so there's one assertion, knows Bob, on the subject Alice. And these can be arbitrarily complex. This is about as simple as it gets, which is why envelopes, even though they're very simple structures, can be very rich. So in this case, where you can see we're actually telling it to use its random number generator to generate a new private key base, which is, again, just key material. And then, or use a seed, which has been generated by Seedtool or something else, and then generate the private key base from that. So here you see the private key base. Here we're actually creating a signer, which is actually, we're actually, deriving the public key base from the private key base, which is a UR signed private key, which is by default a Schnorr key. And then we generate the public key base from that. And then we basically go through the example of actually signing and verifying an envelope. In this case, we're adding a verified by signature assertions envelope. And I'll allude to this again later in my presentation on GSTP, but it's important to always understand that with envelopes, these assertions are on the subject only, in which case all we're verifying here by the signature is the subject, not the knows Bob assertion. And that's generally not what you want. So envelopes allow this feature called wrapping, where you actually, the curly braces here represent this envelope wrapped in another envelope, which allows you to add assertions to the envelope as a whole. And this is generally the correct way to add various kinds of assertions to the envelope as a whole. If anything changes inside the main of the body of the envelope, because this is now this part here is now the subject of the envelope. So any assertions on it, like a signature, require that nothing inside here change. So this is now frozen, or the signature will become invalidated. And then this basically shows the verification process. And then we get into actually signing with SSH keys. And this is the kind of the main topic here, because this is what's new, where we actually are generating a signer and we're telling it which SSH algorithm we want. And SSH keys, if you ever used SSH keygen, you know that these keys always have a comment associated with them, which is often the identity of the owner of the key, which is often the machine, the like username of machine that the key was generated on, or where you intend the key to be used. So that's where you add this here. And then we have, again, a signing private key, but this is actually now an ED25519 SSH signing key. You can also import existing SSH keys from existing key files. So if you have an existing key file, which is often in privacy encoded mail or privacy enhanced mail, PEM format, which is the format that OpenSSH uses, you can import that directly in. Envelope import redirect from this file here, and then if the password is encrypted, if the key is encrypted, which it often is in SSH, in the SSH world, you'll be given an opportunity to actually enter the password, which will decrypt the password and then put it into the UR format that you can then continue to use with the envelope tool. And so this again shows how we have a wrapped envelope here, which is this envelope here. And then we are signing the envelope with the signer that we generated on the wrapped envelope. And then we're formatting the envelope in envelope notation so we can actually read it. And that's what it looks like there. That's a fully signed envelope signed by an SSH key. Same thing, we derive the verifier, which is the signing public key from the signer, which was the signing private key. And then we use the same things we did before with the Schnorr key to verify the signature. And we also specify silent here. The reason why you might want to specify this is because often you want to verify as a multi-step process in your pipeline. And to do that, you want to hand the envelope to be verified to the envelope tool. And then, assuming the verification goes correctly, just immediately hand the result of that off to the next thing in the Unix pipeline, command line pipeline. And so it affords that. But if you don't want that, if you just want it to verify and be silent, then you can specify that. And then, of course, you can export keys. So if the SSH signer I developed earlier, if I want to export that to the PEM format used by OpenSSH, you can do that easily. You can also even encrypt it. So if you wish to encrypt it in a form that will be used by OpenSSH, you can do that as well. And you can also do that with public keys. Public keys have a single line format. Here's the comment. So the comment flows through as you'd expect. This is the same behavior that you've learned to expect from SSH keygen. You can even export signatures. And the final thing you can do is there's a new subcommand info, which you can use on a number of different objects, but in particular with SSH objects like the signer, it will tell you the format. It's a UR signing private key, a human readable description, the algorithm it uses, and the SSH fingerprint, which is exactly what you get back from SSH keygen as well, and even the ASCII art that SSH keygen will show you as a way of quickly visually recognizing your key and distinguish it from other keys. So that's the general functionality that's now made available in the envelope tool. And again, we're going to continue advancing the envelope tool with based on feedback and requests we get from the community, especially those who are sponsors. But we take everybody's comments very seriously. So are there any questions?
Yeah, I wondered, have you gone through all the possible attacks on those signing keys, either the current key attacks or the dead attacks, and how does the system respond to them?
I'm not personally familiar with the attacks you're referring to. I think that if there are weaknesses in the SSH key structures, we've probably inherited them. And I'm not sure we're adding any new attack surfaces. Obviously, we deal with, when we're dealing with private keys in UR format, we're generally dealing with the unencrypted form of those and not the encrypted form. So again, because this is a command line tool and because, command line tools, we expect that our users know what they're doing or are studying best practices. We hope that they will use them in ways that are responsible and don't expose private information. If you want to mention a particular attack, I might be able to address that more specifically, but I'm not familiar with the attacks you're referring to.
Yeah, I'll speak a little bit more about this. Yes, there are a lot of issues with SSH keys in how they're distributed, their use in tofu situations with authentication. But it is, because it is so broadly used, it also has a lot of additional work and efforts to improve those, and we will inherit those improvements. We're largely using well-used libraries for a lot of the fundamental code here. That being said, for instance, there is a group that is meeting in 2 weeks in Vancouver that's going to be talking about adding quantum keys to SSH. In case a quantum computer, arrives, it'll protect SSH keys as well, and we'll benefit, as that evolves and matures. There are, however, some real limitations in general with the SSH key architecture. As someone who's involved with Carry knows, there isn't, really with SSH keys, they're generated individually on individual machines, often using hardware devices. I've been playing around with a wonderful little SSH tool that uses Apple's trust zone. So It will use the Touch ID on your MacBook Pro. Or if you're running on iOS, it will use the Trust Zone and Face ID to secure your keys, your private keys. We don't work with those at this particular point. They're, how the interface to those types of Trust Zone type capabilities isn't as mature as we'd like it to be. Everyone is kind of a handcrafted interface. We hope to have some influence on being able to make that better. But there are also other limitations. You notice that although we keep signing keys separate from key agreement keys, there are a lot of other purposes that SSH keys can be used for. So this is where with using it with envelope and not using the native SSH key mechanisms, but use the envelope SSH key mechanisms, we can add more attributes to an SSH key. So we can do things like, say, it expires. There is no date. There's no standard for when an SSH key should expire. There's no standard for pre-committing to a future SSH key. So I've actually been playing around in a proof of concept where the allowed signers file for a GitHub repo is actually an envelope. And you can basically put future signers as commits to the allowed signers file inside that repo, but then elide them so that nobody can see them until they're needed. So, Carry kind of has some features like this. I can pre-commit a dozen, SSH keys, expire those or revoke those as needed. And then when I need to prove that key number 7 is the one I want to use now, I can basically do an inclusion proof and prove that, yes, this is an allowed signer for this Git repo. This ends up making Git repos, a private ledger, for that particular repo. And that gives you a lot of the kinds of things that Carry does, except for the fact it's a standard format. It works with GitHub. It works with GitLab. You can use it without envelope if you don't need elision by lists, etc. So I think there's some real power for us to be able to offer this if there are people interested in it. I mean, I think where we're at with envelope CLI SSH is it doesn't do hardware, it doesn't do FIDO, it doesn't do a couple of other things of that nature, but it is enough for us to be able to demonstrate that we can do the 80-20 of what Carry and some of the other micro ledger projects do, but with straight up standard well supported, well understood format, which is the Git format, and basically supplementing it with envelope. We'll see if there's some interest in that. I think that it's a powerful solution, but we'll see what other people say and give it a try. So it's really right now oriented towards proof of concepts.
Yep. Really quickly, I'll point out that we're using a very respected crate called SSH Key, which is, provides a lot of the SSH Key functionality we're using. It does have hooks for FIDO and things like that in it. We're not currently using them. But again, if there's community interest in that, then that is a way that we can extend our stack.
Thank you for that explanation. That was great. And I really do think that, for example, in Carry, the inventor there simply says you got to keep your keys secret. That's it, which opens up a whole spectrum for other parties to help you keep your secret. Yep. So definitely we will. I will be on the lookout for keep looking out for the good work you're doing on this side, and hopefully one day I'm able to to combine stuff.
Yeah, and absolutely our next topic there is nothing that says you have to use the kinds of keys and the kinds of material when you're doing, a Gordian depository, shares with, with a request response protocol. So you could create your own. The share servers don't care, other than the fact that, if you put too much data there, they're probably going to want to charge you. So, but we'll talk about that later. Right now, we're going to talk one level below the Gordian depository. Um, so, well, I think Wolf has gone over all of this. We do consider this version 0.9. There are two features in the old C++ version of envelope, which are envelope
I think
diffs.
maybe you want to show the slides, Christopher.
Am I not?
We're seeing your face, not we're seeing your face, not the slides.
Oh, interesting.
No, slides.
Oh, are you
Everything
seeing?
is-
In the slides.
Oh, sorry, it's this new tabs that Zoom has that
Yeah,
was
I have the same problem with Zoom tabs.
My apologies.
No problem.
I'm on the correct
So,
tab now.
So, we don't have the diff support and the mermaid output. So although we've deprecated it, there are times in which I go back to envelope CLI Swift to to do the mermaid output or whatever. The new features obviously generate signer and import and export and info, etc., is all in the Rust code base now. And next steps really is a lot up to feedback from you. We're not planning on doing a lot of work on this other than if someone discovers a bug or in some of my proof of concepts, without feedback from the community that this is valuable, or that our supply chain security for cryptographic code is superior to some of the existing stuff that's out there. There are two sort of breaking changes. If you've already got scripts that are using the old envelope CLI, two of the commands have been replaced to be more specific.
And that's
So,
generally, because privileged keys and public keys refers to private key bases and public key bases specifically, but now we're using more than that to sign and verify. So we've adopted the more general term signer and verifier.
So our big topic for today, and I think really, and this is the culmination of a year and a half or more of work toward a goal of doing this right, is the Gordian Sealed Transaction Protocol. There's a BCR on it that's been around for a while. Envelope request response has been around for a year and a half or so. This adds encryption to it, or it always implied that you could encrypt it, but this is more explicit. What's really powerful and new is there's a real problem, especially with wallets that are hardware devices or have various other kinds of constraints or are at a remote place, that there may be state information that needs to be kept about the process of whatever protocol you're implementing under GSTP, where it could be as simple as, we're at the third round of 5 or whatever, but it could be other kinds of stuff. How do you do that in a fashion such that you don't have to store all of this? And this is both useful from a constrained wallet perspective, where you don't have much room to store all the state. But it also has implications on servers where, they also don't want to have to always process the state. State also can be used to create a number of different types of attacks. So we can also encrypt the state. So we're going to talk a lot more about that in the next half hour or so. But I definitely wanted to thank Foundation Devices, who was the research sponsor for this work. So Ken and team, thank you very, very much. And if you're interested in sponsoring other specific work, maybe you love, RSSH keys thing, or you want to see more of Gordian Sealed Transaction Protocol, let us know. And we'll talk a little bit more at the end, about where do we go from here. This is the underlying thing for Gordian depositories, which allows us to do things like Ledger does for various kinds of seed recovery work, but it can be used for a lot more than just seed recovery, but that's our current model. Wolf, do you want to take over?
Sure. So,
And also
my
begin with
slides.
intro.
Yeah. So I'm Wolf McNally. I'm the lead researcher of Blockchain Commons, and in this talk, I'm going to discuss GSTP, which stands for Gordian Sealed Transaction Protocol. This is a protocol for transaction among various kinds of peer-to-peer and client-server devices, and we'll explain the motivations for it more as we go. But first, I also want to thank our research sponsor, which is Foundation Devices, and I think we have Ken Carpenter here today from Foundation Devices. This GSTP we started developing with it, showed it to Foundation, and Foundation said, "Oh, we might be able to use something," and so they have generously provided funds to enable us to extend this, and the benefits of that are now available to the entire community. So we definitely thank Foundation for sponsoring us in this regard. So I want to discuss briefly our Rust stack. Everything you see here on the right is available on crates.io. The ellipses are libraries or crates, and they're all, everything here is a crate, but the ellipses are libraries and the rectangles are actually command line tools. So in the previous part of this talk, we discussed both the Seedtool CLI and BC Envelope CLI. Christopher a moment ago mentioned the depot server, which is a way that people can anonymously and securely store small pieces of information, could be large, but often small, which are shards of keys, which cannot be keys cannot be reconstructed from them individually, but it's a way of social key recovery. And then these things build on these other crates we have. We also have the DCBOR CLI, which is a deterministic CBOR CLI tool that we have. And so I just want to point out a couple things here that, there are transitive dependencies here that we haven't shown, like SSKR, and pretty much everything else depends on BC RAN for fuzz testing and things like that. So we've simplified the diagram by eliminating the transitive dependencies. I also want to point out that we ourselves benefit from the open source community. That, for example, our BC UR crate adds DCBOR functionality to the UR crate by Dominic Spiker. And so he actually took our spec for UR and our other reference implementations, implemented a new third-party crate. And I said, well, this is great. We don't have to implement our own now, but we do want to add some direct DCBOR capabilities. So we actually created our BC UR crate based on that. And that's what the rest of our stack is based on. But, we definitely thank Dominic for his implementation, as well as other third parties who implemented our UR standard as well. So we're mostly going to focus on this particular crate, the BC Envelope crate. This is where our direct support for GSTP is currently located. The BC Envelope crate, if you look at the cargo.toml file in it, it has quite a few different features. You can basically use it as is, where all the features are turned on by default, and that's fine. And Rust is very good about, in a large code base, compiling, stripping dead code and not including what you don't need in your final thing. But if you want to actually turn off any of these features for specific purposes, you can turn off GSTP, you can turn off encryption, you can turn off whatever you don't want, because Envelope itself is currently an internet draft with the IETF, and it's very spare. It's only got one thing that I would call a feature, other than its general architecture, its hierarchical kind of Merkle tree-like structure. One feature that's kind of inherent to it, which is elision. But all these other things that we're going to be talking about, including encryption, compressions available, although that's not relevant to today's talk, all these other things are features that are layered on top of that. And we have other Blockchain Commons Research or BCR documents that describe each of those features. Those are all implemented in this crate and turned on by default. So you can use those just by, the batteries are included here. So I want to talk about, kind of an overview or motivations for GSTP before we get down into the details. Obviously, if we're describing a peer-to-peer architecture, I just want to acquaint you with make sure we're on the same page regarding certain terminology. We're going to talk about requests and responses, where a request is created by a sender and received by a recipient, and where the response, the roles are reversed of sender and recipient in the response. Fairly straightforward. Where it starts to get interesting is that GSTP is very agnostic about the channel you're using. So that channel could be the internet, using REST or some, TCP/IP, UDP, whatever. Could be Bluetooth, which has, various kinds of security built into it, but also you can use it with no security at all. Could be NFC, either NFC cards or other tools that relay data using NFC. Could be Tor, which is obviously very secure, but again, it's like an extension of the web. Or it could be even something like QR codes, which have absolutely no security at all. Our stack actually includes a way of including arbitrary amounts of data in QR codes using multi-part URs. And that's, the subject of other talks we've done and so on. So, but it'd be nice if you had a protocol that could be equally secure with all these, because, oops, let me do that again. Because the one thing you can say is that because these are all consistent, you have to assume everything is unreliable and insecure from the start, and you'd like something that kind of handles all these cases, which is why we designed GSTP, Gordian Sealed Transaction Protocol. So I want to talk a little bit about the kind of the goals and key components of GSTP. The first is that we want to support asynchronous communications between peers in peer-to-peer environments where there could be multiple peers chatting back and forth, as well as client-server environments. We want to support multimodal transactions, and this means using more than one channel as desired. So you might start with a QR code and then continue with Internet Protocol or Bluetooth or anything like that. We want to support out-of-the-box unique IDs for request response pairs. This is useful for auditing, for making sure that for matching requests and responses across time and space. We want to support bidirectional encryption using public key cryptography, including encrypted multicast. So if you're actually chatting in a multi-way, we want to have multiple receivers. We want to have self-signed requests that include public keys for authentication. And this supports things like trust on first use or TOFU, but also enables you to, immediately see that the person who sent you the message is also the person who owns the private key that signed the message. And this is like a standard feature of GSTP. We very critically, Christopher mentioned this earlier, we want to support message encapsulated state. And this is including having a standard slot for what's called a self-encrypted continuation. And this is a black box to the receiver, but they are obligated to send it back to you so you can continue the computation once you receive their response. And that's also bidirectional. Both, all senders and receivers have the capability of including self-encrypted continuations. And then we also, in this continuation mechanism, we implemented expected response ID and continuation timeout mechanisms to avoid things like replay attacks. So that's also very useful. And generally speaking, I've always been a huge fan of idempotent actions, which are actions which, if repeated, cause no additional effect. So our architecture for envelope, for GSTP and things like that are designed to, while we don't require it, we certainly encourage the design of APIs and architectures that rely on idempotent actions. What are the benefits of this? Well, we want to reduce state management. We want to, our continuations allow peers to offload private state information into the past messages, minimizing and ideally eliminating the amount of local state needed for ongoing tasks. And this hopefully, when combined with idempotency, increases fault tolerance. We want to make this more scalable. So especially like in client server situations, it's not always the case where adding more servers gives you more bandwidth, because if they all depend on a set of shared state in a database, then there's database contention and so on. Whereas if all the state you need to continue the computation is included in the request that only you can access because you encrypted it to yourself in a previous step, any server can handle the request. And so that allows what's called horizontal scalability, which is, adding more servers gives you linear increases in capacity. And obviously security, self-encrypted continuations maintain the privacy and integrity of the sender's state information. And then we include the expected response IDs and timeouts and continuations to help prevent manipulation of continuations for like replay attacks. And efficiency obviously is a big concern as well. So envelope is a binary structure, and it's designed to be deterministic and minimalistic. So you only need to pay for what you use. So continuations and responses enable things like pagination, streaming, and incremental processing of large result sets. Obviously, that if you have used certain REST APIs, you might get back a token from the server, which basically says, if you want to continue this pagination of this, send back this token. Same idea here, but actually much more flexible and very secure. So to lay the foundation for this, I want to discuss requests and responses as distributed function calls. And remote procedure calls are nothing new, but I want to make clear how we've implemented them using our stack and how it fulfills the goals that we've just discussed. So I'm going to start by looking at just a Rust kind of a generic function signature here. It's an asynchronous function, which means it can be paused and handed off to other threads while it happens. It just has a generic name do it. It has two different arguments of two different types. The ellipsis indicates it could have more. And then it has a result, which in Rust basically is either a success type or a failure type. And this is all highly relevant to what we're translating this to. Of course, this applies pretty much to any language. So this is how that appears as an envelope. Now, earlier in this meeting, I discussed the general structure of envelopes. Envelopes always have a subject, which in this case is the function identifier, and then a set of assertions, which are predicate object pairs, which essentially make assertions about the subject. And that translates in this case to the function identifier, and the arguments are assertions on the function identifier. These chevrons here essentially are shorthand for CBOR tags, because again, this is a human readable form of a CBOR structure. So it's important to realize that we're translating it to text, and so we could just spell out the name. This is function, and surround this with parentheses. This is parameter. But because we do this so much when we deal with what we call envelope expressions here, we have a shorthand, which is these double chevrons. And because this is a human readable format, you never need to type these. It's always for output. This is not a round tripping format. But it is essential to understand what's going on inside envelopes as you construct them and use them. And so this envelope format is widely used. But we're going to come back to envelope expressions in a minute. But this is essentially what an envelope looks like that translates this. So what do we do with this from here? So we want to encapsulate this in a request. And to do this, we generate a random ID. This is what we call an apparently random identifier, which is like a super UUID. It's actually 32 bytes, which is twice as long as a UUID, even though we only show the first four bytes of it for brevity here. And this is a CBOR tag. This is also a CBOR tag. So it's nested CBOR tags showing that this array is a request. And this is the subject of the envelope again. The subject has one assertion, which is the predicate body, and then this as the whole expression as the object. I'll come back to that in a moment. On the response side, it's the same basic pattern. There's the same array, the same ID, because it's the response to this. However, it's tagged response, not request. And then it has either the predicate result with the success type or the predicate error with the failure type. So again, I'm going to kind of hammer this home a little bit here. This is the subject of these envelopes. In one case, on the left side is request with the array. On the right-hand side is response with the array. And each of these envelopes has exactly one assertion on it. In the first case, it's body with the expression. In the other case, it's result with success, or error with the failure. I want to point out here that this is the predicate, which is the single quotes indicate this is a known value, which in envelope parlance is just actually it's in a small integer. So if you see things enclosed in single quotes, it's not a string, not like you'd see in a JSON file. It's actually like 2 or 3 bytes maybe from a 64-bit known address space. You can use strings as well, though. There's no reason why you can't use strings. There's no reason why you have to use known values. So again, this kind of speaks to the flexibility of envelopes. I want to point out that because this is a common mistake people make, that on the left-hand side, that's not the object. There's predicate object pairs. This is just the subject of the actual object. And so if you want to see the whole object of that assertion, it's the entire envelope expression. All right. And these are examples of complete assertions. So just a single argument assertion or a result or error assertion. All right, so now we're going to look at things from the sender's perspective. We have a request, which has the assertion, which is body, and the expression, which is the object of the assertion. And now we want to add the things that make Gordian Sealed Transaction Protocol useful in what it is. The first thing we want to add is an authentication layer. We want to make sure that the receiver knows that whoever sent this owns a private key, which is essentially the key that's been signed with. So if we're going to actually provide that public key, so we add an assertion called sender public key, and we add our public key base to this. This is a Schnorr signing key. As I mentioned earlier, we support SSH keys now, but our stack currently uses Schnorr keys for everything else where you don't need SSH keys. And then we also add a sender continuation. Now, this is what we want to receive back when we actually are, because we're the sender in this case. If we want to, when we receive back the response to this, we want to continue our computation without storing state locally. We need to encapsulate that state here. And that state, again, what you're seeing here as the capital S state here, that can be any envelope. It means it can be arbitrarily complex. But we're just using an identifier for the type here. But the thing is, we're going to encrypt it. So this is now encrypted back to ourself, as indicated by the light blue, which is the sender's color here. This is encrypted to ourself, only we can read it. So we're going to send this, and the receiver is going to be obligated to send it back to us. We are also going to include the receivers, the recipient's continuation, which is what they sent to us that's encrypted back to them, as indicated by the orange color. So this has always been a black box to us. We received it maybe at some point in the past, but it's optional. If we didn't receive one, we don't attach it. But we don't know what's in here. It's only for use by the receiver. The next thing we want to do is actually want to verify the envelope by adding a signature. And as I mentioned elsewhere, because an assertion only is on the subject, and because the subject is just this string here, the request of the request ID, all that would do is verify this. We want to verify the whole envelope, however. So this isn't the right way to do this. What we're going to do, right, that's the actual subject. So we're going to remove that, and this is how we do it correctly. So we want to sign the whole envelope. And to do that, we actually want to wrap the envelope in another envelope. And this is a standard feature of envelopes. You wrap an envelope, and then now the subject of the envelope is the whole previous envelope. And now we can add its own assertions to it. So now when we add the verified by signature, then we are now, we've basically made it impossible to modify any of the contents of the subject, which is the area in curly braces, without invalidating the outer signature. All right, so now we've got a signed request. We've also included our public key base. So with nothing more than that's here, the receiver can verify that whoever is identified here must have also the corresponding private key. So that's the main thing we've done there. And this is useful for trust on first use and things like that. We'll discuss that more a little bit later. The next thing we want to add is our layer of encryption. So again, if we just like when you sign an envelope, that's an assertion only makes an assertion about the subject. When you encrypt an envelope, you're only encrypting the subject. And so if you encrypted this right now, you'd basically have the encrypted envelope with the verified by signature. And it's important to realize that with envelopes, the signature would still verify, because even encrypted structures in envelopes, they declare their hash of the unencrypted value. So so the signature still verifies you when you transform an envelope in this way, but we want even this to be entirely hidden because it could lead to correlation attacks that we don't want. So we're not going to encrypt that. We're actually going to do the same thing we did before. We're going to extend the subject. We're going to assign the whole envelope. We're going to wrap the envelope, and then we're going to, which basically makes that the whole subject of the envelope. We're not going to add any new assertions to it yet, but then we're going to encrypt that. And now we have a symmetrically encrypted envelope that's it. It's all it is the envelope. Now, I said symmetrically encrypted, but we want to use public key cryptography here. So what do we do? How do we deal with this? All we do is we add one assertion, which is called a sealed message. And again, as indicated by the orange color here, this is created using the recipient's public key. It also includes an ephemeral sender. That now it's not our public key in this, but it's an ephemeral sender we create just for the sealed message, and we attach this has recipient to it. And this basically means that when the recipient receives it, they can use the ephemeral sender's public key, which is included, and their private key, use key agreement to find the actual, to create the, to recover the symmetric key that this was encrypted with. So that basically allows you to, this is called static, ephemeral static, ephemeral static public key encryption, basically. So because on our side, we've just created ephemeral sender, we're using their static public key. And so we've encrypted this entire message in a public key way. And we can add more than one of these assertions too, if we want. And I mentioned encrypted multicast. This is where if you wanted several receivers to be potentially decrypt this message, you could add more has recipient assertions with sealed messages that encrypt the symmetric key just to those recipients, and then that set of recipients could also decrypt this message. All right, so this is what is actually sent to the sender. So sent to the recipient. And on the recipient side, now they're going to reverse this process. They're going to use their private key, recover the symmetric key, and decrypt the original envelope, leaving this. So now we stripped off the encryption layer, and now we have the authentication and request. So the next thing this does, and this happens automatically in our stack, is the next thing it does is it extracts the sender public key you see there, and then checks that against the verified by signature and makes sure that those match. And that's an important part of the process to avoid spoofing and things like that. But it's pretty much provided as part of the batteries included nature of our Rust stack. So once that happens, that's stripped off, and now you have the request. The next thing you can do is you have what's called a sealed request structure, and then you can parse out the various parts of that, including the ID, the sender, the peer continuation, which is the encrypted black box that you're going to pass back to the other side again, the state, which starts out encrypted, but now because you're the recipient, you can decrypt it. It's automatically decrypted for you using your private key, and now you have everything you need to actually execute the remote procedure call, to do it with the two arguments. Once you do that, then you compose your result, which is either success or failure, which is, again, before uses the response, the same ID with the response tag, and the result and success type assertion. And then we reverse the process again. We add the sender public key, our sender public key in this case, not the previous sender's public key. We add our state continuation, but we encrypt it. And again, this happens automatically in our stack. And we add the recipient continuation, which is what we're passing back to the other side for them to continue their own computation. And finally, we wrap it and verify it with our signature. And then we encrypt that and give it the has recipient sealed message so that the new receiver can decrypt it. So it's exactly the same process on both sides. So we briefly want to discuss the trust on first use, or TOFU pairing, this is what our Gordian depot uses. It assumes that there's people out there who want to back up their seeds, and they want to store a small piece of data like an SSKR share, which they need to retrieve a quorum of later to recover their highly sensitive seeds, but they don't want to trust any one party with the whole seed. And they don't necessarily want to do this as a public service. People may want to make it so you don't have to pre-register for an account. So how do we handle this? So in this case, we have a client server architecture, and the server starts by publishing a discovery message. And the discovery message, the main thing that it needs to put in the discovery message is its public key. And this is not an encrypted message. This is essentially something that's open and discoverable if it's a standalone device. This could be published as a UR with an envelope. If it's a standalone device, it could display a QR code, which is then read by a camera. Or if it's like the depot server, for instance, it provides a single GET call, which allows you to get the public key. And then from then on, it's all post calls with just envelopes, and no third party can tell whether it's a request or a response or whatever, because it's all just UR envelopes going back and forth. Once the client has the server's public key, and I should mention that any of these channels can be mixed and matched for this. So the discovery packet can be sent one way, and then further communications can be carried on through any of the other channels that you want to support. So then the client now can compose that full stacked request that you saw with the authentication encryption layers, and then the server now has the client's public key, because that's included in the client's message, and so it can send back a response that can only be read by the client. So that's how you bootstrap a trust on first use kind of conversation using GSTP. So I want to walk through a little bit of code, and I don't want to belabor this because not everybody reads Rust in the audience. So I'm going to go kind of quickly, but just want to show how it looks in code when you strip off these layers and you process an incoming request from, say, the server's point of view. This is a function called handle request string, and this assumes that you can see here that it's receiving a UR string, and it's also returning a UR string. So this is the top level of a server that receives strings and outputs strings as its responses. And most of this is error handling code here. But the important thing here is the from UR string, which actually converts the UR, which is just text, into the binary structure, which is an envelope, by stripping off that UR. So now it has the request. And now that handles it down to the handle request method here, which receives the envelope as an encrypted request. As you can see, it's still in the encrypted state. It hands that down to another function called handle unverified response. And mostly this is here to handle errors from that. Notice that there's a function called new early failure here. It's used here as well. This is where an error occurs, say, for example, in decoding the UR. Maybe the UR was corrupted. You don't know anything about it. You don't know who sent it. You don't know what was in it. You can't tell because you can never get past that. So you have to send back a message that basically says this was an invalid request, or there's some kind of other message, error in like you couldn't decrypt it for some reason. Like it was for example, it was sent the wrong, it was encrypted to the wrong public key. So you couldn't decode it because you have the private key, you have a private key, but it wasn't the private key that was necessary. So these are causes of early failures. So then that's passed down to the handle unverified request, which then, and a lot happens here. This is the sealed request, try from the encrypted request. And this actually strips off the outer two layers and actually verifies that the signature is created by the person who actually enclosed their public key. So you know that much. You don't know that they're in your database. You don't know that whether you're doing trust on first use or not. That's for you to decide at this lower level where you're actually handling the verified request. But at this point, you can parse out all this information, the ID, the function, the sender, public key, the peer continuation, the seal, and then basically create a sealed response. And this is the next level below. This is where we call handle verified request with the sealed request. And then this is where we generate the response. There's two ways of generating a response, either in response to the successful execution of this, or if there's a failure. Now we can pass back a fairly detailed error message where a wrong parameter was added, or the person is unknown in the database, or whatever. So this is where, so we again have the okay and error responses here. The last thing before we send back our response is that we want to add there's two last things. One is we want to add the authentication layer, and that's where we're saying we're actually creating this sealed response, which includes our public key. And then finally, we want to create the actual sealed envelope, which we're passing our private key here, so we can actually use it to create our encryption layer. And we also are adding an expiry date. So what this does is this actually puts into our own continuation the last date which our continuation can be used. So that's checked up here. So if there's one of these that arrives and the continuation has expired, you can say, sorry, it's too late to use that. That's one of the two checks. The other one that it's not shown here is expected request ID. That's because this is a response, not a request. But the client generally would put an expected response ID into that, which the server will return as part of its continuation, and that will be checked by the client as, oh, well, I was expecting this particular response ID, but your response ID is different, so I have to reject this. Okay, so one layer deeper, we actually handle a verified request where the unencrypted, completely parsable request comes in, and as you can see, this is where it's dispatched. And I just wanted to point out that there's, in this case, for example, the start recovery function. This is where a user says, oh, I lost my public key, or I want to use some other method, that a fallback method to recover my share. And this case is a case where the server is actually saying back, okay, here's my continuation. Here's what the start recovery needs to actually do, change rotate your public key to a different public key. And then this is encrypted and handed back. And again, this is just a black box to the client, but the client has to hand it back to you at some point. And that happens here in finish recovery function. So this is where the server basically unwraps the state and basically says, oh, okay, this is what I need. And so I'm going to call, I'm going to actually finish the recovery, rotate the public key. But if that state is missing, it can't do it. So, again, the interplay is anything you need to continue. This is the start of the function. This is the continuation of the function. And the difference is this may come back through some other method, like through a phone number or through an email or something like that, something that has nothing to do with how this request was originally made. But that's the second factor that requires a user to authenticate so they can actually rotate their key. All right, sorry if that was a little bit disjointed, but that is basically the walkthrough of Gordian Sealed Transaction Protocol. And I hope we've done a pretty good job of explaining why we think this is a great way of doing things, and kind of demonstrating its flexibility and the fact that it incorporates a lot of best practices into a very understandable structure. So I'm open for questions.
Now, would you go back to the benefit slides?
Yeah.
So the key thing here that I want to point out is that, this is the foundation for a wide variety of protocols. Obviously, our first use case is the Gordian depositories, but can really be used for a wide variety of other things. I'm hoping to use it with Git repos for supply chain security. It can be used in a wide variety of protocol situations. And many of those protocols many of the protocols can also take advantage of the general benefits of envelope, with in particular elision. So, we can have a situation where, I send you something, we establish a tofu, but then you decide, well, I'm only going to give you some information back because you have not fully authenticated. Here is how you can fully authenticate. And then, you basically can do a couple more rounds in there where you're slowly revealing additional information to each other to improve the trust that you have between the two parties. And maybe you don't even necessarily go all the way to the end of the protocol. You have sufficient information to be able to meet your risk model or whatever it is that's appropriate for you at that particular point. And although there might be additional steps that someone can go through, it is sufficient for you to take action based on the protocol and do the function that you've been requested to do. So I think there's a lot of opportunities to use state, to use elision, to use other things. I mean, even as an example, I've been trying to puzzle out, there could be, when you actually put when you create, say, an envelope inside a Git repo, it actually might have elided your private keys. And you go, well, that seems kind of stupid. That's, why would I put my private keys into a public Git repo? But that would then allow you to, for instance, to prove that the key did exist and in your past, or allow you to do some different types of things. And because it's just a hash and a proof of existence, you can basically do integrity checks in a very stateless fashion. I think there are a lot of opportunities here for advanced protocols that I don't really see, anything else that supports it with the level of ability to do privacy, to do progressive trust, and other different types of techniques out there. So this really, I think, is a foundation for a huge number of opportunities.
I would point out that because the envelope itself is a hierarchical structure, and because if you elide a branch of that tree, you're leaving a hash in place that is a cryptographic commitment to everything that was in that branch. But you can reveal just the top level of that branch without revealing everything down inside it. But at each step, that when you reveal that, you've basically not just revealed that yes, what was in there that you were committed to, but also, you can reveal just parts of it and leave the rest elided too. So you haven't revealed everything yet, but you're still committed to what's there.
Also, we're taking advantage of a variety of in the same way I was talking about SSH demonstrating not necessarily cryptographic agility, but cryptographic flexibility. We have this same kind of flexibility in the future for how we do the permits. I mean, right now we have two ways to recover the symmetric key that lets you unwrap an envelope. We have the way that was demonstrated here with the sealed message with the ephemeral private key, with ephemeral keys. But there's also the SSKR method where you basically, I have to assemble things from multiple places. There could be additional ones in the future that, for instance, used Frost. where it required a quorum of parties to basically agree in order to unwrap the next level of the envelope. So there's a lot of interesting capabilities there. Ken, did you want to just make a quick statement or anything? We thank you for your support for this research. Oh, he left. Okay. Again, we want to thank Foundation Devices for helping us get to this point, and all of our sponsors in the past that helped us build the foundation underneath this of Envelope and SSKR and Seeds, etc. We are at 4 minutes past when we should be ending. So any last questions before we continue? And record this and save this for everybody. I am not hearing anything. Espen, Irfan, any last comments?
There's definitely some nice comments in the chat. Hank thanked us, and Ken thanked us as well before he dropped off.
Okay. Well, thank you again. So next month, we are going to have as one of our focuses the discussion on Zoom is hiding my button. We're going to be back to the first Wednesday date, so it'll be Wednesday, August 7th, and we'll be using the Zoom URL that we've been using for previous first Wednesdays. We're going to have a presentation on BIP 85, and hopefully have a discussion about the implications of that. And then I'm hoping to have a demo of how to use SSH with Envelope with Git. So a more specific, detailed proof of concept for that. If you have something you would like to present about wallet interoperability, whether or not it's a question or a proposal or a concern, let us know. We'd be glad to give you some time to discuss your specific needs. So just let us know before the Wednesday before the 7th, which I guess is the 1st or the 30th. So thank you very much, and see you in 4 weeks. Thanks.
Thank you, everybody.
Thank you.